Yeah, and my name's Robert Main. I'm a research associate here. And so here's a little, to start, here's a picture of an FRB. You know, the FRB is located in its host galaxy, in its local environment. And what happens to it as it passes between its emission site and our telescope, which is in the Milky Way. On the way, it passes through the intergalactic medium. So all of this space contains plasma, cold plasma, in this case, cold meaning non-relativistic. This will cause dispersion, as I'll show, which is magnetized, and this will affect the polarization, in particular through Faraday rotation. And this cold plasma is inhomogeneous, which will result in scattering and scintillation, as I'll show. So just a bit of a backing, why do we see any such effects on a radio signal? Well, the index of refraction in a cold plasma is slightly less than 1. So this here, index of refraction, I have as mu. And this is the difference from 1. This first term is the plasma frequency over the observing frequency. The plasma frequency depends on the electron density. So this will give you a frequency-dependent group delay as you travel through this plasma, which depends on the electron density over the observing frequency squared. And this value is much, much less than 1 typically. You see it's 8.5 kilohertz if you have plasma densities of about 1 particle per centimeters cubed. And we'll see soon that in any typical astrophysical place, in particular in Milky Way or the IGN, the values are much less than that. So the second term I have with a plus or minus. This is a frequency-dependent group delay between polarization states, or between the left and right circular polarization. This value is, again, much, much less than 1. And this will result in a slight phase delay between polarization states that we will see. And then, of course, I started by introducing the index of refraction. That will immediately tip people off to the idea that, oh, light will be able to bend. So any spatial gradients or any differences in the plasma density will result in the bending of light, and that'll result in scattering and scintillation. So, all right, let's go through these. Let's go through these one at a time. So dispersion is related to that first term, and we can characterize it with the dispersion measure, and it's the total integral of the electrons along our line of sight. So this is the total column density of electrons. It's a catch-all. It's additive for all of the plasma you encounter. And that means that when you measure the time delay, which will have this frequency to the -2 dependence, we measure the total column density between the burst and us. So here's a simulated burst. I put it in. We have it here. It's emitting at the source at the exact same time across frequency. So applying a dispersion measure, we get this characteristic, well-understood sweep. And if you measure exactly what the sweep is, you have measured the dispersion measure. So now I've added some magnetic field lines. I mentioned the plasma is magnetized. This results in the second term I talked about, which is a slight delay between the left and right circular polarizations. This manifests as a phase, beta, which I have written as beta. It's measured in radians per meter squared. So already you have an idea. If you measure the wavelength of your light, or you know the wavelength of your light, you have your rotation measure. This will tell you how much it'll rotate between the polarization states as a function of wavelength. So again, this is the same burst, and applying a rotation, looking at the polarization states. So now we have Q and U. So these are the two linear polarization states. You can see the oscillation between positive and negative, and you can see that they're out of phase. So here's an animation for how that can look. So this is right there. You see that's when you have the correct rotation, but you're going to see if you scroll through different rotation measures, you can see the oscillation becomes faster. And then when you have the exact right rotation measure, everything is derotated. The phase is aligned with 0, and all of the power, which is in the bottom right, is able to sum up, and you'll recover your true peak. So I'll just let that play again. It's going to scroll past the peak, and now it's going to go back. All right, so that's the effects of Faraday rotation. So the one other effect I mentioned, now I've added some squiggly lines to the plasma density because it's inhomogeneous, and that'll cause the bending of light. So this bending, the total bending angle you can get depends on the change in the column density over delta x, so over some spatial scale. So the smaller your spatial scale, the smaller your plasma fluctuations, the larger the bending angle of light. And this results in a path length difference. And this results in a time delay as it takes light a longer time to reach us, just simply due to geometric delays. The bending angle, since it's related to dm, it also has a frequency to the -2 dependence. And then the time delay is related to the angle squared. So you get a much steeper dependence of this scattering time delay with frequency, typically something like frequency to the -4. So now the burst, which was very narrow originally, what you'll often see is something like this, where the different scattered paths of light, if you have many such scattered paths, this will form a characteristic tail. Each of these will arrive at a later time, and it'll broaden your signal. And this is the fun part, or this is, to many, this is one fun part of this, is that FRBs appear to be point sources. And so each of these copies is the same electric field, but slightly delayed. And exactly as Calvin was just explaining with VLBI, you have the same electric field, they're delayed in time. They will interfere. So this is referred to as scintillation, and that gives you this interference pattern that you see as a function of frequency. So I wrote delta F. In this case, I mean the scale of the scintillation pattern is inversely proportional to the time delay. So the larger path, the more delayed paths will give you finer fringing in frequency. Okay, so yes, this is a GIF. Instead of showing the two screens as I have above, just looking at the simple case where you have the observer, and we're looking at these different scattered paths. The top right is a dynamic spectrum of a burst as you get more and more scattered paths, and you can see the fringing get finer and finer. I'll let that play one more time. And the bottom right are the image positions as we would measure them on a telescope if we could resolve the images. All right, so that's in quick strokes how you can understand the scintillation pattern. So to put some rough physical values, so I mentioned these various effects that manifest in effectively any fast radio burst you'll see. We have our dispersion measure related to the total column, the rotation measure, which is the total column density weighted by the magnetic field, and of course the bending angle, which has to do with the change in the column density over space. The IGM is very tenuous and hot. This will add to the dispersion measure because there's such a large space. However, the rotation measure is weighted by the magnetic field, and as well as the bending angle is weighted by your coldest, your densest, clumpiest plasma. And these will be strongly weighted into host galaxies or regions of higher electron density. Okay, so just a quick summary before we get into what we learned from these. So fast radio bursts pass through cold plasma, which is magnetized and inhomogeneous, resulting in, for any typical FRB, usually this array of propagation effects that you see. Okay, so what do we learn from this? So the rest of the talk, I'll give a little bit of a flavor of what these effects learn, what they've taught us about FRBs in the field. It's a non-exhaustive list, but you'll hear plenty about that in the rest of the conference. The hope is that this gives a bedrock and a bit of a flavor about what you can learn. So starting with dispersion measure, that's largely why the field kicked off. That's largely why we're here. That let us know that fast radio bursts are extragalactic. So this is the first discovered fast radio burst, the Lorimer burst from 2007. And you see this dispersive sweep. You can measure that very precisely. You can measure a dispersion measure of 375 parsecs per centimeters cubed. And we can say, well, along this line of sight, we know pretty well the plasma density or the plasma column in our own galaxy. and it should be nowhere near this value. So to have encountered this much free plasma, it must be out of our own galaxy. And so that was already remarkable. So how do we know this? And this is one of the main uses of dispersion measure. To start, let's say, what do we already know from pulsars? So we have thousands of known pulsars that are distributed throughout the Milky Way. Again, the dispersion measure is the total column density of plasma, typically measured in parsecs per centimeters cubed. So very roughly, if you know the plasma density in centimeters cubed, you can divide that and you can get the distance. So a dm plus the electron density tells you the distance. Conversely, if you measure the distance to many known calibrators, in this case pulsars, and so you know the distance, you know the dm, each one of them tells you the plasma density along a specific line of sight. And through many known pulsars with measured distances, you create a three-dimensional map of the plasma in our galaxy. And you can see here, that's what's plotted on the bottom. This is from the NE 2001 galactic plasma model. This is an edge-on view, so it's in galactic coordinates. And you see, far away from the plane, there's very little contribution. So these contours are at 50 and 300, I think. So if you're far off of the plane, you expect a very little dispersion measure, a very small contribution to the dispersion measure. So using that idea, you can replace the word pulsar with fast radio bursts. And now instead of being populated throughout our galaxy, they're populated throughout the universe. So using this idea, you can map the universe's baryon content. And there's a whole block on this, and there's another talk today. But using this, you can probe the baryonic content of our universe, and you can use FRBs as a cosmological probe. So then the dispersion measure relation there gets factors of redshift and includes cosmological parameters. This relation here at the bottom is now referred to as the McCart relation. And that's what it's showing. It's showing the dm as a function of the redshift for several localized fast radio bursts. And the black line there was the prediction from the cosmic microwave background measurements. And they generally agreed, which was showing that using FRBs as a probe, you can actually see the majority of the baryonic content of our universe, and it's matching the predictions that we have from cosmology. And as we get many more FRBs with measured redshifts, you could actually create a three-dimensional map of the intergalactic medium, similar to what we've already done with pulsars. So this is again one of the main driving factors, and this is why we want to localize many FRBs to many host galaxies. Okay, so then what do we learn from rotation measure? So one of the main things that it tells us is it's helped reveal that FRBs, or at least some FRBs, are in very special environments. So again, the rotation measure integral looks very similar to the dispersion measure, except it's weighted by this magnetic field. So if you know the dm and the rm occur in the same region, you can simply relate them. And in the typical units that we measure them, rm in radians per meter squared, dm in parsecs per centimeters cubed, you can take the ratio of the two, and it basically tells you the magnetic field in microgauss. So in the slide above, the Milky Way, a typical value is about a microgauss in the ISM. In the intergalactic medium, it's much less than that. So in this bottom case, this is the first repeating FRB. And when the rotation measure was measured, it was tremendously high. It was about 10 to the 5 radians per meter squared. The dm budget, the amount of material or the amount of plasma that could be in the host, is something like 100 units, perhaps a bit more or less, but not orders of magnitude. And this suggested that the source had to be already in a fairly special environment. The magnetic field had to be at least about a milligauss, far more than you expect in typical ISM. And this already suggested, along with the persistent radio source next to it, that perhaps it's in a young, dense supernova remnant or a highly magnetized magnetar wind nebula, or in our own galaxy, we've seen high rotation measures like this near our central black hole. So, right, so what do we learn from scattering and scintillation? In broad strokes, I would say that it gives us a window into the smallest scales. So again, the bending angle that we see, it's weighted by the spatial scale. So the more tightly you can pack your plasma, the wider your bending angles are. And in the case of pulsars, we've been able to map we're able to see the actual substructures that, or infer the substructures that bend light to cause the scintillation that we observe. And these are sub-AU scales, so almost planetary scales of plasma. And similarly, that's just from scattering. But for a source to scintillate, it must be point-like. So for the exact same reason that Kelvin explained, an extended source becomes washed out with VLBI. If you have an extended source, it'll wash out this interference pattern because each of them will have effectively a different diffraction pattern that'll superimpose and destructively interfere or average out. And what do I mean when a source must be point-like? Again, it's perfectly analogous. We have the exact same electric field from multiple deflected paths, and the interference between them is just like a two-slit or n-slit experiment or an endpoint interferometer. The spatial scale will be lambda over L, and in this case, L can be AUs or tens of AU. And the analogous statement is always stars twinkle and planets don't. Or you could say FRBs scintillate and radio galaxies don't. And again, I'll briefly touch on this if I have time. You can use scintillation and scattering to localize our plasma structures, either through the interplay between multiple screens or directly through VLBI or by using the time axis. So here's a little animation showing how scintillation constrains source size. So I've put in an image on the right and I've made it gradually get bigger. And I'm passing it through the exact same scattering screen. And so on the left is its spectrum, and you see these bright peaks and troughs. That's due to interference. That's the scintillation pattern. And as it gets larger than the resolution of the screen, lambda over D, that's what I have denoted as this orange circle, you see that the scintillations are dampened. So by measuring the degree to which a source is modulated, you can either constrain the source size, or potentially, if you're ambitious and brave enough to interpret your data, you might be able to even measure it. And using this exact same idea, many of you have encountered this idea where you can use the presence of multiple scattering screens and using the two-screen constraint to constrain or localize where the scattering occurs or where the plasma fluctuations are. This uses the exact same idea that a source must be point-like to scintillate. But now, because you have two screens, you have a scattering tail. That means that's an extended source. And then that scattering tail is fully scintillated by a second screen. Both screens must be point-like to each other. So that broadened scattered image must still be point-like to the second screen. And what that means is that you have to put the two screens sufficiently far away from each other that they still follow this point-like constraint. And that gives you a constraint on typically a constraint on the product of the two distances. This is just a characteristic value. And then knowing the plasma distribution in our own galaxy, say we know that the scattering is probably somewhere within about a kiloparsec in our own galaxy, we constrain that the scattering has to be within the host. And in some cases, we can get much tighter constraints. And we'll hear about that later this week in some of the science talks. So how am I doing for time? I think 5 minutes or so. Anyways.
Yeah, you have to.
Okay. So, right. So I was talking about all of these effects in isolation, but of course it's all the same. It's all the same plasma. These effects are intertwined. And sometimes through the combination of them results in other measurables. So one of these is the fact that the same plasma that's scattering light, the different paths that the light has to take don't have to encounter the exact same plasma. They don't need to have the same dispersion. And they don't have to have the same rotation measure. And necessarily, they must be slightly different. If they're sufficiently different, then your main burst that you're measuring is sampling many different paths, each encountering different magnetic fields and different plasma densities. Each of those will have a different rotation measure, and then the phase oscillations won't be aligned. And similarly, you'll effectively average over many different oscillations, and your polarization signal will disappear. So that's what I've shown here. This is in the bottom left, these are many images sort of isotropically distributed on the sky. I've put a rotation measure gradient across it. And on the right, I've plotted the polarized spectrum. And you can see at high frequencies, where scattering is not so prevalent, you have a fully polarized signal. And it very steeply depolarizes as a function of frequency. And the different lines are just different models that you can use to try and predict how that depolarization should occur. All right, in the remaining few minutes I have, so all of this could apply to a single fast radio burst that you observe. But this, we know that some fast radio bursts repeat. And of course, that's part of the drive of this conference. It's the 10-year anniversary of the first known repeating FRB. What happens if you use the time axis? What happens if you set the FRB in motion? So for one, scattering and rotation measure, these can change with time, and these can change quite drastically with time. One great example where you see all of these effects is FRB 2019-0520B. So in the bottom left, you see a very clear scattering tail of about 8 milliseconds. A few minutes later, the scattering tail is gone. So for it to change that rapidly, the source must be seeing a very different environment over a very small time scale. So that suggests that the inhomogeneous plasma causing this must be extremely close to the source. And I think physically it must be less than a parsec, perhaps much, much less than a parsec away from the source. And similarly, the rotation measure was both very large, implying a high magnetic field, but changed sign, which again is difficult in your standard interstellar medium. And one of the possibilities is that this is the magnetized wind from a binary companion. Oh, and similarly in the bottom right, you see the polarization fraction as a function of frequency. It's depolarizing due to the interplay between variable rotation measure as a function of the viewing angle as seen through scattering. And the last effect I wanted to show is, let's put scintillation in motion. And it's fun to give this after Calvin's talk because this is again exactly analogous to VLBI. So I showed how time delays manifest in this interference pattern or fringing as a function of frequency. But each of these scattered paths samples a different velocity vector, either of the FRB or of the Earth. And that gives you a relative Doppler shift that actually causes your light to go in and out of phase as a function of time. And so I'll show the exact same animation, but now instead of the burst spectrum, this is how the spectrum of the burst would change as a function of time. And the bottom right shows the Doppler shift and the geometric time delay of each of these images that I'm having. And you see that it's going to play again. You see that this pattern in time becomes finer as the longer paths are introduced. So this spatial scale, or this time scale of the interference, it's related to these Doppler shifts, and that directly measures the velocity weighted by the distance of your scattering material. So if you can measure this, you actually have a way to probe the dynamics of your source. And this isn't just in simulations. I wanted to point out that you can actually do this for an FRB. So this is well studied for pulsars. It's the whole field called scintillometry, which is the idea to make precision measurements of the ISM and of your source dynamics by using scintillation. But we've actually measured scintillation arcs in highly active repeating FRBs. And this is one such study using the FAST telescope by Ziwei Wu and others. And this is a scintillation arc for 2022-09-12A. The scattering is very likely in the Milky Way. So we're probing the Earth's velocity. I guess this is another proof that the Earth goes around the sun. But if you're able to do the same using a scintillation pattern from the host galaxy, you directly probe the FRB's motion. And you might even be able to show, for instance, a binary motion, or at the very least constrain its transverse velocity. So yeah, that's a quick overview, hopefully a good bedrock for what we're going to hear in the coming week of the different ways that radio light is affected between the source and us. And on that, I'll leave it on my final slide, and thank you.
Like 5 minutes earlier.
Well, gives time for questions.
Yeah, it does. Yeah.
All right. So questions. Awesome. Yeah, so you had this slide, or sorry, I'm Mawson, for the people that are online. So you had this slide that basically showed the differential rotation measure as a function of so you had this, right, well,
I'll repeat
what are you
it.
doing about that? Yeah, right, so you had this, I think it was on slide 19 or 20, the differential rotation measure as a function of viewing angle. Uh, is this, is part of this effect due to the Doppler delay that you have for a source that's in motion?
Um, yeah, so Mawson asked, so I have this plot and it shows that the rotation measure changes as a function of the scattering angle. And he asked if this is related to the Doppler shift that I showed later, which gives you the time scale of scintillation. Um, Short answer, the depolarization, no. The depolarization comes from the fact that you're averaging over all of these angles at a given time in your scattering tail. That said, um, if you could plot this in a delay Doppler map, you would see that the ones that are positively Doppler shifted would have an RM in one direction and vice versa. And I think there's actually a talk later this week that tries to put all of these constraints together.
Yeah.
But so short answer, the depolarization doesn't come from the Doppler shift, but you could see this effect. You could see the same gradient as a function of the Doppler delay if you could decompose it that way.
And so the reason that I ask that is that we often, I suppose, have this degeneracy of that some of our constraints are it's difficult to know whether they apply if a screen is one-dimensional. But it seems that if a screen is one-dimensional and the source motion is orthogonal to the dimension of that screen, that then some of these effects like RM would disappear. And so in the circumstance where you have those observables, you might be afforded the capability to distinguish between things that we thought were degenerate.
Yeah, that's right. It definitely breaks the degeneracy. There is still an angle there between your RM gradient and your velocity axis.
Yep.
But a 1D screen does look different than a 2D screen and how it depolarizes. So, oh, I guess I didn't repeat the question. Mawson was asking if you could break the degeneracy between, I guess, the axis of motion and the RM gradient, and if that could tell you about the geometry of our scattering screen.
This is an online question from Aniket Prasad. How would the scintillation pattern be different from the Milky Way and the host galaxy?
That's a great question. So yeah, so how would the scintillation be different between the Milky Way and the host galaxy? So in some ways they're symmetric. So for the same time delay will create the same interference as a function of frequency. If you can measure how the scintillation changes in time, they're sensitive to different velocities. So the scintillation in our Milky Way is sensitive to the velocity between the Earth and the plasma. The scintillation in the host galaxy would be dominated by the velocity between the source, the FRB, and its plasma. So they're probing different physical velocities. Similarly, which source has to be point source-like is different. So if the scintillation happens in our host galaxy, it has very little resolution, so to speak, at the FRB. Whereas if the scintillation is occurring in the host galaxy, then the FRB must be point-like, and that's where the constraints on the source size come from. So in some ways they're symmetric, but not others. Also, if the scintillation occurs in our Milky Way, it might just be, in some cases, the scattering can be milliarc seconds or tens of milliarc seconds. So you could actually resolve it with VLBI. So you could break this degeneracy using, for instance, chime outriggers or even other existing VLBI networks.